Hello everyone. We are going to get started with an interesting journey of natural convection. So far there was always a fan, someone was driving, someone to cool it, fan or a pump. But now the driving force is going to be the temperature difference itself. So that is what is natural convection. There is no pump. So the temperature difference itself is the pump. So we will understand that. So to understand, we will take up the question, what is natural question, and we are natural convection, and we will define the coefficient of volume expansion. Then we shall derive the equations of motion for natural convection over a vertical plate. And in the same way what we did for a flow over a flat plate, we will do the scale analysis for Prandtl number less than 1 and greater than 1 to obtain the scales of thermal boundary layer thickness, Nusselt number, velocity, thickness of the wall jet, and distance from the wall to the velocity peak. All of these values we will get from scale analysis. Of course, orders, not the values, orders. Then we shall do dimensional similarity for natural convection boundary layer equations to identify the non-dimensional numbers, and then the criterion to decide whether the heat transfer is forced or natural, and few standard correlations for natural convection I would give, but many would be available in various textbooks. I would not be giving all the correlations, but I would suggest you the books. And the representative problems on natural convection, one or two, quickly, I will not solve step by step, but I will give you the feel of the problem. And then the interesting thing with all these basics, how I can apply to the real life, that is vertical channel flow with walls of a channel at constant surface temperature, where the channel flow is occurring because of the natural convection only, and optimal cooling of a stack of vertical heat generating plates. That is, if you want to stack your circuit boards in your laptop or computer, not laptop, in your computer, how do you stack, how close they should be so that the cooling is effective, that can come from these fundamentals. And we have derived all this for constant wall temperature. We will extend that for constant heat flux using scale analysis. I am not going to teach the integral approach or the similarity approach. Similarity approach and integral approach has been taught by Professor Arun for external flows. So the similar thing you can do it for natural convection. So we believe that with those basics you will be able to catch up with the fundamentals yourself. So the natural convection, if you just see here, there is a hot egg and there is a cool air. The cool air is getting heated up, and as it gets heated up, its density is very small, so the warm air moves up. This is what is called natural convection current. So because there is a continual replacement of the heated air in the vicinity of the egg by the cooled air. So here there is a natural convection current, there is no pump here, that's why it is called natural convective heat transfer. So natural convection to occur, it is required, two things are required. One is density difference, another one is gravity. There is no gravity in space, therefore there is no natural convection heat transfer in the space, even if the spacecraft is filled with the atmospheric air, because there is no space, because there is no G. There is no G there. Even if you have air, there is no G, so there is no way that you can have natural convection. So in heat transfer, primary variable is temperature, therefore we need to express the net buoyancy force in terms of temperature difference. So the density difference would be expressed in terms of temperature difference, which requires the knowledge of a property that represents the variation of density of a fluid with temperature at constant pressure, that is volume expansion coefficient. So to write the heading as natural convection, and if I take up volume expansion coefficient, volume expansion coefficient beta is equal to 1 by V dV by dt at constant pressure, or minus 1 by rho d rho by dt, because rho and V are inversely proportional, that is why negative sign has come, d rho by dt at a constant pressure. If you just see this figure which is there in the slides, you see in the first figure in the left hand side, you have 20 degrees Celsius, 100 kilopascal, 1 kg you have collected. Now what did you do? You increased, this is the air which is filled at 20 degrees Celsius. You have increased the temperature from 20 to 21. So what has happened? The volume has expanded, the piston has moved up. So del V by del T at constant pressure has increased. Now you see the next figure, you have 20 degrees Celsius, 100 kilopascal, 1 kg, it has become 21, but the increase in the volume is not much. So the substance on the left hand side which will have larger beta than the substance which is on the right hand side, because the change in the volume for a given change in the temperature is less at a given pressure. So that's what is the definition of beta. We will need this while we are deriving. So now let us take up equation of motion for a vertical plate. Equations of motion for natural convection over a flat plate, which is vertical plate. If I consider this as a vertical plate, this would be my boundary layer, and this is maintained at a constant temperature Ts, and the temperature distribution, if I were to plot, it would be something like this. This is temperature profile. Now if we take the velocity profile, it would be something like this, because at both the ends V should be 0, because this is stationary fluid. The far away from the boundary layer, it is a stationary fluid, unlike flow over a flat plate at T infinity and P infinity. And this is my velocity profile, and constant surface temperature is what I have taken. If I consider the assumptions, what are the assumptions? What I am going to assume is that the flow is laminar. Natural convection flow is laminar. I am taking it as laminar, and it is two-dimensional, and the flow is steady, things are not varying with time, and the fluid is Newtonian and constant properties, but with an exception that the density variation I will consider only in the body force. Okay, this is little difficult for the students to understand, but you should insist that I am considering the density difference only in the body force. If I don't consider that body force itself is not there, means there is no natural convection. So that's why I have to consider there, although I have made that the properties are constant. This is where students will have doubts, they will ask questions. We have to stop here and say that it is the density difference is considered only in buoyancy force. If I don't consider this density difference in buoyancy force, if buoyancy is not there, then there is no question of natural convection. So the buoyancy force is the driving force. This is what is called Boussinesq approximation, Boussinesq approximation. So we are making this Boussinesq approximation and going ahead. So if you, and as I said, it is constant properties, the equations would reduce to del u by del x plus del v by del y equal to 0, rho of u del u by del x plus v del u by del y equal to minus del p by del x plus mu del squared u by del x squared plus del squared u by del y squared. This is x momentum equation. Y momentum equation would be rho u del v by del x plus v del v by del y equal to minus del p by del y plus mu del squared v by del x squared plus del squared v by del y squared minus rho g. What is rho g? That is the body force. Why negative? Because if you recollect, this is my vertical plate, my g is downwards. So that is why the force downwards in the negative y direction, so it is minus. So minus rho g, and the energy equation is U del T by del x plus V del T by del y equal to alpha into del square T by del x squared plus del square T by del y squared. Okay. So now let's try to do the scale analysis. Okay. So x is of the order of delta T, that is the thermal boundary layer thickness, and y is of the order of height of the plate, and v, let's take it as v only. So because vertical velocity will be higher than the horizontal velocity, unlike our external flow where flow over a horizontal plate, forced convection. So from the continuity equation, del u by del x plus del v by del y equal to 0, that is u upon delta t is of the order of v upon h, which implies that u is of the order of v delta t by h. Let's call this as equation 1. Let's keep it like that. Now let us take up x momentum equation. If I take up x momentum equation, the scale of, so I have just pulled out rho this side, I will write the scales directly. What is the scale of u del u by del x? Just now I wrote u scale is v delta t by h. So v delta t by h into del u by del t del x, so that is also v delta t by h up into scale of x is delta t. Okay, so that is the first term, comma v scale is v only, del u by del y is v delta t by h, v delta t by h, and the scale of y is h. This should be of the order of minus 1 by rho del p by del x. I am going to keep it like that only, I am not going to change that, comma nu u is v delta t by h into x is delta t squared, comma nu v delta t by h into 1 by h square. So as you can notice here, this is delta t by h cube. Delta t is very much less than h. So this term can be neglected. Similarly, if you see here on the left hand side, this is v square delta t by h squared, so it is the same. So you are going to get v squared delta t by h squared is the scale on the left hand side, is of the order of minus 1 by rho del p by del x, comma nu v by h delta t. So this is my second equation coming from x momentum equation. Now let me take up y momentum equation. If I take up y momentum equation, the scale of y momentum equation is u. The scale of u is v delta t by h, and the scale of v del v by del x, that will be v, and the scale of x is delta t, comma v is as it is, and again v is as it is, and y is h, is of the order of minus 1 by rho del p by del y, comma nu v by delta t squared, comma nu v by h squared, comma rho g. That is okay. So you get, so this, the left hand side is going to be v squared by h the scale is v squared by h, is of the order of minus 1 by rho del p by del y, comma, this out of these two terms, this can be neglected because 1 by h squared is at any rate lower than 1 by delta t squared, comma, nu v by delta t squared, comma, minus rho g. No, rho wouldn't be there because I have divided it by rho. So you get this as equation 3. Okay. So now let me just try to get the feel of this pressure in a little different way. So just to recall, U we have gotten as V delta T by H, and V squared delta T by H squared is of the order of minus 1 by rho del P by del X, comma, nu V by H delta T, this was X momentum equation, and the Y momentum equation is V squared by H minus 1 by rho del P by del Y nu V by delta T squared, comma, minus G. Okay. So now let me write dP equal to del P by del X into dx plus del P by del Y into dy. Divide throughout by dy. dP by dy equal to del P by del X into dx by dy plus del P by del Y into dy by dx. dy by dy, that's it. So you divide throughout by dP by dy, you get del P by del X into dx by dy plus upon dP by dy plus del P by del Y upon dP by dy. Just take this term alone. So del P by del X into dx by dy upon dP by dy is of the order of, you see, del P by del X, what will be the order of this? Del P by del X order would be same as the viscous term, so that is nu V by H delta T into rho. Actually I should do, but I don't try to do that because denominator dP by dy also I will take the scale as nu V by delta T squared, so that way rho would have gotten cancelled out, I wouldn't have made any mistake. So what is the scale of x? Dx by dy. The scale of x is delta T and the scale of y is H. So you get, what is this? You get nu gets cancelled out, V gets cancelled out, delta T gets cancelled out, delta T by H whole square. So that means whole of this term can be neglected. So that means del P by del Y equal to dP by dy, which implies that pressure is a function of only y but not x. So if you retake the x momentum equation, if you come to x momentum equation, this term itself is not there. So if this term is not there, means we have taken the same order this, so this also would vanish. If right hand side is not there, means left hand side is not there, so we can neglect from this, we can say that neglect x momentum equation. If you recollect, in flow over a flat plate, in external flow, we had neglected y momentum equation with the same arguments, but here it so turns out that x momentum equation gets neglected. So you have del u by del x plus del v by del y equal to 0, rho into u del u by del x plus v del u by del y minus of del P by del Y plus mu del squared V by del Y squared minus rho G. I just want to write this rho G in terms of temperature, that's why I have again written these equations. But let me remind you, just we found that this del P by del Y is equal to dP by dy, and with the same I can write this as dP infinity by dy. If you recall what I had taught, I divide this into viscid zone and inviscid zone. and the pressure is the pressure impressed upon the boundary layer from the free stream. So that is dP infinity by, that's how the inviscid region and the viscid region get connected with each other. With the same argument, I can write dP infinity by dy, del P by del y equal to dP infinity by dy, and dP infinity by dy equal to minus rho infinity into G. This is what we have found, that is the hydrostatic pressure. You have studied this in fluid mechanics. So you substitute this, you get rho infinity into G plus mu del squared V by del y squared minus rho G, that is equal to mu del squared V by del y squared plus rho infinity minus rho into G. If you recall, beta equal to, just let me write this, u del u by del x plus v del u by del y. I will just try to write this in terms, this is v, this is v, u del v by del x plus v del v by del y. So now beta equal to, we have defined it as minus 1 by rho d rho by dt at constant pressure. So that is minus 1 by rho, rho infinity minus rho upon T infinity minus T. So rho infinity minus rho is equal to beta rho into T minus T infinity. I have substituted negative sign there. So I get my equation as u del v by del x plus v del v by del y equal to nu del squared v by del y squared. Please notice that I am dividing throughout by rho, plus beta rho, rho gets cancelled out because I have defined, so divided by rho G beta into T minus T infinity. This is my now x momentum equation. This is my buoyancy force. Buoyancy force. So we have the equations. I can rewrite, I will rewrite once again so that we are summarizing this. Del u by del x plus del v by del y equal to 0, and u del v by del x plus v del v by del y equal to nu del squared v by, see I have made a mistake in the previous equation, this is x squared, mu x squared, whole of this is x squared, I am sorry about that, this is x squared. So you have del squared v by del x squared plus g beta into T minus T infinity. The energy equation is u del T by del x plus v del T by del y equal to alpha into del squared T by del x squared plus del squared T by del y squared. With the same argument, actually I can neglect del squared T by del y squared also, but for now I am keeping it because I have not taken the energy equation yet. So u equal to v equal to 0 and t equal to Ts at x equal to 0 and v equal to 0 and t equal to T infinity as x tends to infinity. So these are my equations which we have derived for incompressible fluids, that is I have taken the density variations only in the body force, nowhere else. So, okay. So with this, so we are able to find the equations for the natural convection for flow for a flat plate which is maintained at a constant temperature. So if we recollect again back doing scale analysis, from the momentum equation what do I get? U upon the scale of the x is delta t and v is v and this is h. So u is of the order of v delta t by h. There is nothing new, we have done that already. And This scale we have found that this is v squared by h is of the order of nu v by delta t squared comma g beta delta t. Okay, this is for x momentum equation, and the y momentum equation is, no, this is the x momentum equation. Then v we have found from the energy equation. Let's find the energy equation. From the energy equation we will be able to find the v. U is from here v delta t by h delta t upon delta t comma v delta t by h is of the order of alpha delta t by delta t squared comma alpha delta t by h squared. This can be neglected because this is very small, and this delta t gets cancelled out. So you get v delta t by h is of the order of alpha delta t by delta t squared. So v is of the order of alpha h by delta t squared. So these are the three scales which you are going to get. So you got u, you got the x momentum equation, and you got the scale of the v. So now if I take this equation, that is v squared by h is of the order of nu v by delta t squared comma g beta delta t. Now I know v is equal to alpha h by delta t squared. Just now I derived it. So if I substitute that, alpha h by delta t squared whole squared into 1 by h equal to, is of the order of nu v by nu by delta t squared. V is alpha h by delta t squared comma g beta delta t. So if I divide this, so what do I get? Alpha squared h upon delta t to the power of 4 is of the order of nu alpha h upon delta t to the power of 4 comma g beta delta t. Multiply throughout by h cube by alpha nu. If you multiply throughout by that, so you get alpha squared h upon delta t to the power of 4 into h cube by alpha nu is of the order of nu alpha h by delta t to the power of 4 into h cube by alpha nu comma g beta delta t h cube by alpha nu. Actually h cube, this whole of this is the definition of Rayleigh number, that is RAH, Rayleigh number based on h. This is Rayleigh number. So what do I get on the right hand side? I get h to the power of 4 upon delta t to the power of 4 into alpha by nu is of the order of h to the power of 4 upon delta t to the power of 4 comma Rayleigh number. So this is h by delta t to the power of 4. This is 1 by Prandtl number because nu by alpha is my Prandtl number. So this is of the order of h by delta t to the power of 4 comma Rayleigh number. Okay. So if I divide throughout by Rayleigh number, I am going to get h by delta t to the power of 4 Prandtl to the power of minus 1 Rayleigh number to the power of minus 1 is of the order of h by delta t to the power of 4 Rayleigh number to the power of minus 1 comma 1. Why did I do that? Because buoyancy is essential, so that I made it as 1. I cannot neglect it. So this is inertia, this is friction, this is buoyancy. So let's stop this module now, and in the next module we will take up further for Prandtl number less than 1 and greater than 1 and how to work it out. Okay, thank you.